In this video, I am going to discuss a very basic fundamental problem so that the students get an idea of how to use the potential energy criteria for equilibrium and consequently determine what type of equilibrium the system is in, whether it is in stable, unstable, or neutral equilibrium. So this problem has been taken from R.C. Hibbeler. It is an unsolved problem. The uniform bar AT has a mass of 20 kg. You can see that there is a uniform bar AT which is hinged about point A. Its length is equal to 1.5 meters and the mass given is 20 kg. If the attached spring is unstretched when theta is equal to 0, the spring will be undeformed or unstretched state when theta is equal to 90 degree. Now see, in this case, the theta is given with the vertical. Okay, the bar is making an angle of theta with vertical. So theta is equal to 90 means bar will be completely horizontal when theta is equal to 90. Okay, this means theta is equal to 90 degrees. Also note that the spring always remains in the vertical position due to this roller guide. You can see that there is a roller and this roller is free to translate in this guide. Therefore, the spring always remains in the vertical position. Okay, assuming if this bar is rotating in the clockwise direction, obviously the roller will move towards left, but the spring will always remain in the vertical position. Similarly, if the bar had been rotating in the anti-clockwise direction, obviously this point B will shift towards this. Okay, and the spring will and the roller will also move in the right direction so that the spring always remains in the vertical position. That's why this roller which is attached to the spring is free to move in this guide. Okay, the only possible motion is translation. Okay, either towards left or towards right, so that the spring always remains in the vertical position. Now, one more thing to note is that when theta is equal to 90 degree, okay, when that is when the bar is horizontal, the spring is unstretched. So one can clearly see this will be the unstretched length of the spring, that is L naught. That means in the current state, when the bar is making an angle of theta with this vertical, there is a stretch in the spring. And if I extend this point B horizontally, this will be the extension in the spring. Therefore, this is the total length of the spring, that is L plus L naught plus X. So in this case, the spring is in its stretched state. Okay, at this angle theta, the spring is in the stretched state or in the deformed state, having an extension of X. So it's clearly seen from the figure. Okay, when theta is equal to 90 degree, the spring will be undeformed. And as this bar is moving in the clockwise direction, that is, as this theta is decreasing, okay, from 90 to 0, the stretch is going to increase. Okay, at theta is equal to 90, the stretch is 0, and at theta is equal to 90, the stretch will be maximum. Okay, so this thing is clear from the figure. Now we have to investigate the stability of the bar when it is in the equilibrium position. Okay, we have to establish the stability. So let's rub this off. One thing is clear to us: when the bar is completely horizontal, that is, the bar is making an angle of 90 degree. This will be the position of the bar when theta is equal to 90 degree, and obviously the spring will move towards right. Okay, it's pretty much obvious that in this position the point B is here, and when the bar is at theta is equal to 90 degree, okay, obviously the bar would be rotating in the anti-clockwise direction. Okay, when we are moving from theta to this 90 degree. Okay, so it's quite obvious that this point B will shift somewhere here. So at theta is equal to 90 degree, this point B will actually be here and the bar will be horizontal, and this will be the spring. Okay, this is the spring. So one can see that this is the undeformed length of the spring, and the extension of the spring will be this distance. Okay, this distance will be the extension of the spring. Okay, so now what is our goal? Our goal is to calculate the our goal is to make the potential energy function of some variable. Okay, here the variable will be theta. Now we can write the potential energy terms, that is, just moving to the next slide and writing the potential energy terms. So first of all, if we draw the free body diagram of this bar, we can see that if this is the length of this bar is equal to 1.5 meters, therefore its center of gravity will be lying somewhere here, and the weight force will be acting in the vertically downward direction. Okay, so this is going to be the weight force. Also, one can see that since the spring is in the stretched position, there will be a restoring force in the free body diagram that will be shown in the upward direction. Okay, because the spring is in the stretch, therefore the restoring force will be acting opposite to that of the displacement. And there is a hinge at A, hinge support. Therefore, we will have horizontal reaction at A, and we are also going to have a vertical reaction at A. Okay, but see here, what are the active forces? These reactions aren't going to contribute to the virtual work. Okay, if we are taking the example of the virtual work, these these forces, that is the hinge reactions, aren't going to be contributing to the virtual work. Therefore, they can't be treated as the active forces. Now, in this case, the active forces are the weight, okay, and the spring force. I can write here the active forces are weight and spring force. Okay. Therefore, whenever we have the conservative forces, okay, both these forces are the conservative forces. So whenever we have the conservative forces as the active forces, there we can use the potential energy criteria. Therefore, first of all, I have to write the potential energy function. Therefore, the potential energy function will consist of both the gravitational potential energy and the elastic potential energy. Now, see, for this, for finding the what we call as the gravitational potential energy, we need to specify the datum. Okay, therefore, let me specify this horizontal a line passing through the point A to be the datum. Okay, so what is the distance of the center of gravity from the datum? This can be clearly seen. Okay, first of all, we can clearly see that this center of gravity is lying below the datum. Therefore, the gravitational potential energy will be negative. That will be equal to minus YW, okay, multiplied by the distance of the center of gravity from the datum. Okay, so minus sign is because the center of gravity is below the datum. And what is the distance of the center of gravity from the datum? It's clearly seen that I will show it with green color. This distance, okay, this distance is the distance of the center of gravity from the datum. Okay, I can represent this distance by y plus this elastic potential energy. Now, this elastic potential energy is independent of the datum. If the spring is in the stretched state, it will have elastic potential energy that is equal to half of k x square. If the if the spring is unstretched, that is, there isn't any deformation. Therefore, the potential energy due to the spring or the elastic potential energy will be zero. So this elastic potential energy is irrespective of the datum. It only depends whether the spring is in the deformed state or in the non-deformed state. Now it's clearly seen that the spring is in the deformed state, and that deformation is this distance x, okay? Because this portion here, it represents the unstretched state. That is, this position is equal to x naught, rather L naught, which means the undeformed length of the spring, plus this x, okay? This is the extension. Let me represent this by x, okay? So it is equal to 1 by 2 k x square, okay? Now we can see that if you see this equation, you can see that this potential energy function depends upon this distance y and this distance x. but indirectly both y and x are function of theta. Y can be represented in terms of theta, and this x can also be represented in terms of theta. Okay, therefore this is a single degree freedom system because this theta is sufficient to specify the complete configuration of the system. Okay, now it's quite easy. The potential energy function will be equal to weight multiplied by this distance. Okay, this distance. So one can clearly see that if this is theta, then this angle is also going to be theta. Okay, and this center of gravity will be at the distance of, okay, 0.75. Okay, that is, this length is going to be, this inclined length of the center of gravity from the point A is going to be 0.75 meters, because this is a homogeneous bar or the uniform bar, and the total length is equal to 1.5 meters. Okay, fine. So one can clearly see that this distance is going to be, 0.75 cos theta plus 1 by 2 k. The spring constant is given as 2 kilonewton per meter. Therefore, this will be equal to 2000 Newton per meter. And x, now from this right angle triangle, okay, this is again going to be a theta, and this is a right angle triangle, and the distance of the point B from point A is equal to 0.5 meters. Therefore, this distance x will be equal to 0.5 cos theta. And we have a square with this, therefore it will be squared. Okay, now the weight is equal to, mass was given as 20, and this is 9.81, 20 g. Okay, this is 0.75 cos theta plus, so this will be 1000 into 0.5 square, that will be 0.25, that will be equal to 250 cos square theta. Okay, now let's solve it a little bit. This potential energy function, now this will be equal to minus 147 point plus 250 cos square theta. Okay, so let me write this potential energy function again. It's equal to minus 147.15 cos theta plus 250 cos square theta. Okay, so our goal was to represent the potential energy as a function of single independent coordinate, and we have represented the potential energy as a function of theta. Okay, now for equilibrium, we can take its first derivative with respect to that independent coordinate, and this should be 0 for equilibrium. So from here we get that minus 147.15, the differentiation of cos theta will be minus sine theta plus 250, the differentiation of cos square theta, that is, it will be equal to twice cos theta, and the internal differentiation of this cos theta, that will be equal to minus sine theta. So this term has to be 0. Now from here we get that 147.15 sine theta plus, rather we will have a minus here, and this can come out, so it will be 500 sine theta cos theta. So this has to be 0. Okay, so from here we can take sine theta to be common, In the brackets, we will have 147.15 minus 500 cos theta. So this will be 0. So from this equation, we will get two values of theta. Okay. Either sine theta is to be 0, which implies theta is equal to 0 degree. And another condition of equilibrium is that 147.15 minus 500 cos theta, this can also be 0. From here, we will get that theta is cos inverse of 147.15 divided by 500. So this value of theta comes out to be 72.9 degrees. Okay. So there are two positions when the system will be in equilibrium. One is when theta is equal to 0. Okay. So theta is equal to 0 means that the bar is completely vertical. Okay. The bar is completely vertical. Theta is equal to 0 specifies bar is in vertical position. Okay. And there's another value of theta which is near about 73 degrees. That will be another equilibrium position. Okay. Now what type of equilibrium does theta is equal to 0 represent, and what type of equilibrium theta is equal to 72.9 degrees represent? That can be found out when we take the second derivative of this function. Okay. So I can write the function again, dv by d theta. dv by d theta is equal to 147.15 sine theta. Further, we have minus 500 sine theta cos theta. I can take 200, okay, sorry, this 2 to be common, okay. I can break this into 250 multiplied by twice sine theta cos theta. So this will be 147.15 sine theta minus 250 sine 2 theta. Now I can compute its second derivative. That is the derivative of second order. This will be equal to 147.15. The differential of sine theta is cos theta minus 250. The differential of sine 2 theta is cos 2 theta, and we'll have an internal differentiation of this 2 theta which is equal to 2. So this function is equal to 147.15 cos theta minus 500 cos 2 theta. Okay. So we can find, we have to check at two positions. The first position is theta is equal to 0 degree. So when theta is equal to 0 degree, we can substitute 147.15 cos 0 minus 500 cos 0. Okay, cos 0 is equal to 1. Therefore, we will have 147.15 minus 500. So this will be equal to, it will be a negative value, and that will be equal to minus 352.85. And since this result is negative, okay, so this result is negative. What does it correspond to? It corresponds to unstable equilibrium. because negative, okay, negative means, okay, when the second order derivative is negative, it means it is the condition of maximum potential energy, and that corresponds to unstable equilibrium. Now we can check the same value at, we can check for the second order derivative when theta is equal to 72.9 degrees. So from here we will have minus 500. Okay, so it was actually 147.15. So 147.15 cos of 72.9 minus 500 into cos 2 theta, that is, okay, so once we solve this, it comes out to be around 456. And since this comes out to be a positive value, so this corresponds to stable equilibrium. Okay, we have seen these conditions earlier. So this was just an introductory problem, so that the students get used to uh, how to make a potential energy function and how we equate it to zero to get the conditions of the equilibrium. Okay, that is at theta is equal to 0 and theta is equal to 72.9 degrees, the system would have been in equilibrium. And further we investigated regarding the stability of the equilibrium by calculating the higher order derivative, that's the second order derivative. Okay, so we'll come up with a few more problems in the next lecture. Okay, thank you.